Thanks everybody for coming in and listening in today. My name is Greg Rueff. I work for Vogt Power in the Aftermarket Services Department. I run the proposal group, and I'm going to present two success stories today. These are just two projects that we've executed in the past year or so that kind of highlight our approach to aftermarket services. That is, approaching the project from a whole outage standpoint and correctly accounting for planning every step, from designing and engineering to manufacturing to the actual outage work. I've seen a lot of plants that split up the work into material and installation portions, and that certainly works. But I just want to highlight some of the benefits that comes from capturing the whole scope under one contract and the drawbacks that occur when you don't. So let's see. There we go. So the first case study that we're going to look at is an Attemperator retrofit. So on this, sorry, was there a question? Okay. So the existing Attemperator was a typical candy cane design, is what we call it. The HRSG was a 3-wide unit, and each width had a discrete Attemperator loop. This was real common for certain OEMs in this time frame in which these plants were built. This plant was built around 2002. So you'll see these all over plants of this vintage from this OEM. And this design has stayed still pretty prevalent. You can see how the piping comes out of the top casing here from each of the 3 widths. Again, it's a 3-wide, and then it sprays up. So this is how both the HP and the reheat Attemperators are configured. They both kind of spray up in these candy cane loops. You can see the reheat Attemperator in the background with the arrows. That's what it's pointing at. And then the HP Attemperator is in the foreground, going over the top of the reheat Attemperators. So these Attemperators, they were the integral Coates-Vulcan spray valves. The spray injection point was in the upward direction at the platform elevation. So spraying up is good, right? And it's a lot better than spraying down, which is also something that was done way back when. What we found is that gravity is really influential in the spray flow velocity and impingement. So typically we don't like to spray down anymore, as gravity actually hurts that issue. So spraying up is good. In this arrangement, it allowed for easy platform access to the spray valve. It's right there at the drum level elevation, so it was very convenient. But these Coates-Vulcan spray valves, they were integral spray valves, and by that we mean the nozzle spray pattern is not fixed, but it varies as the nozzles are covered and uncovered, kind of by that probe. This is opposed to a non-integral probe style spray nozzle, where the spray pattern is fixed and there's an external control valve. With this integral style, there is no external control valve. It's all one piece, the spray nozzle and the control valve. So these spray water valves, they've historically had so many problems in high temperature applications. Anytime you have a moving part that's in a 1050 to 1100 degree F application, you're just asking for problems. These things have seized up, and you lose control. They've straight up broken off, and then you find the probe lodged in some header somewhere downstream, and then you're just dumping water straight into the pipe. It's a nightmare. But that wasn't even the issue here. The issue here was there was insufficient straight length for the injection water to completely atomize. It just wasn't long enough. So this led to water droplets falling back down on the inlet side and carrying over on the outward downstream side. So even though you're spraying up, there is any excess entrained water in the system, it's going to drop down either side of the inlet or the outlet side, both of which lead to the module heating surface headers. So any water droplets that aren't completely evaporated are potentially going to cause problems. And remember, there's 3 of these things potentially dripping water on all 3 headers across the width of the unit. So water impingement is always going to lead to cracking. The site had previously tried to remedy the problem by replacing the Attemperator liner with stainless steel, but the root cause was insufficient spray water atomization. You know, the first thing that often goes is the liner, and you know, it's typical to kind of think that's a problem. So they tried to beef that up and say, okay, we're going to put a liner in there out of a more robust material, but it's not addressing the root cause, and that ultimately failed as well. So the water impingement, it continued to cause problems on the upstream header to crack at the header to piping connection. So that's actually what you can see in the bottom right of this presentation, that picture there. The header to nozzle connection is where the crack initiation began in the attic space of the unit. You can see it circled there, and the little red arrow is pointing to it. I mean, that's going to be one of your most susceptible areas anyway, right at the weld, and that's where they saw that crack initiation. These other pictures that I've included on this slide, they're from other installations where we've seen the same issue, water impingement on various parts of the Attemperator. You know, whether you completely destroy the liner, which is a sacrificial piece, and it's intended to be impinged upon, or you completely quench an elbow, water droplets are the enemy. So water impingement has also led to the tubes to bow in the downstream reheater harp in this instance. So the crazy thing is, this plant actually limped along okay for a while. It was only when they switched their operating profile from relatively base loaded to a cycling plant and also running at lower loads than before that things really got out of control. And that's the thing, a bad design can survive a base loaded plant for quite some time before you really run into a problem, because you run in those problem areas so infrequently. You pass through them quickly. You're not running there for an extended period of time. You know, at ISO condition, most OEMs, they don't even design their heat balances for spray flow because it's not thermally efficient. You know, at your 68-degree day, that's when you design your Attemperator to be off. You hit your temperature dead on without any spray flow. That's the ideal way to design it. Your Attemperator is supposed to be off. It's the off design cases, the off design ambience, the GT loads where the Attemperator really needs to work. It's the one by cases and the low load conditions that really test the design. So the solution here was for VPI to redesign the loop entirely, accounting for those startup cases and those low load cases where the spray demand can be the greatest and it results in the longest retention time. So this means you need to look at all your old PI data across the entire ambient and load range, and also at your new operating points that you get from your GT OEM. And I call these your envelope operating conditions. They end up being the design point of the system. So if your design can work at those envelope cases, those boundary cases, they can work at every point in between. So for a gas turbine like the 7F machine that likes to reach its isothermal limit at lower than 100% GT load, it's looking at this point at your hottest ambient day with your highest GT exhaust mass flow that you get your maximum Attemperator spray point. So this establishes the maximum spray flow your control valve needs to pass, and it sets the C sub V of the valve and establishes the turn down. So you need to know the cases that you have to capture the full envelope of your operating conditions. And don't forget, you know, your GT exhaust temperature, it can vary plus or minus 25 degrees from what it's supposed to be doing. And you need to account for this. So all of this needs to be taken into account. Also, depending on the mass fraction of the spray percentage to steam flow, that can dictate your retention length. If you're spraying a whole lot of water, right, and your ratio exceeds 15%, you probably need more length in your loop, not just to the first bend to prevent impingement, but you also want to pay very close attention to where that thermocouple or where those three thermocouples are to make sure you're not wetting them, to make sure you're reading dry steam. Your Attemperator controls are going to go all over the place. As soon as a little water droplet gets on one of those sensors, it gives you an erroneous reading. So you need to make sure they're placed accordingly. They're not going to get wetted, and they'll give you good information for your controls. And then you need to look at your one-by cases. That's where you only have one HRSG feeding your steam turbine in a 2-on-1 train or a 3-on-1 or 4-on-1 train. Remember, this is where the pressure is at its lowest. Recall, as pressure goes down, velocity goes up. So this is the case that sets your steam piping sizing. And it also indirectly affects your retention length, since retention is based on velocity. So what does all this mean? It means you can either make your line longer or larger, or sometimes both, whatever it takes. So what we did here is we combined all three widths into a single Attemperator loop using a ring style injection nozzle with a non-integral valve, and we upped the pipe size to a lower bulk average velocity. So we kind of did all of the above. So you can kind of see this in the isometric GA on the right of this slide that traces the flow path of the new Attemperator as it goes through the path there. So combining all three widths into one line, it obviously requires a larger line because we're now running 3 times as much steam through it as before, right? There were 3 discrete loops before, we're now combining them into one. But now we only have one control point, and only one place where we have to worry about maintenance and inspection of equipment, one failure point. So see that as a benefit there. These ring style injection nozzles, they really seem to be the go-to solution for high temperature Attemperator applications. I'm not going to say that the nozzle style can't work because they can, but you know, they really only seem to stand up long term, you know, in applications of like 900 degrees or lower. Once you really get above that, they just don't seem to last, my experience. So, you know, it's obvious this OEM was trying to skimp out on the piping costs and the routing. I mean, look, I get it. It's probably P91 piping. It's expensive. But, you know, the redesigned Attemperator loop, it needed so much length that we had to drop it all the way down the side of the unit, as you can see there. We needed that length to get the retention time that we needed. But also notice in this solution now, if there is any entrained water in the steam line, it would have to be carried up against gravity all the way to the top of the loop, and then go down one of those feeder nozzles to get anywhere close to impinging on heating surface, which is what we really want to protect here, right? What's more likely is that any entrained water is going to be collected in the drain pod, which is at the lowest point on the entire loop. So we've eliminated one of the failure points and hopefully protected the harps a little bit better, which is much more difficult to replace than just some external piping. We'll talk about some harp retrofits here in the second presentation, but generally I'd say piping is a little bit easier than a harp retrofit. We don't have to cut open the casing. So since VPI and TEIC had been awarded this job on a turnkey basis, we could coordinate internally the best routing and fabrication methodology for maximum constructability. You know, when we redesigned this thing, we didn't just say, oh, I need 150 feet of new piping and place it indiscriminately. We're able to consult with our partners and collaborate on a routing that worked technically, but was also constructive. So we were able to design for both at the same time because we were mutually invested in both of us succeeding. So, you know, as much piping as practical was prefabricated on site into the larger spools before the unit came down to maximize the short outage window. But I'm actually going to turn it over to my colleague Tim now from TIC to kind of talk through some of those details.
Yes, good afternoon, everybody. So my name is Tim Holland. I'm with Teic Construction. I am the gas operations manager. We mainly focus on HRSGs, but we do also do other gas units, auxiliary boilers, simple cycles, even gas conversions. The way this project came about is the customer, of course, had the need and went to Vogt Power and wanted a turnkey solution. This was on 2 units, and these units were to be performed simultaneously. So during the planning stage, we were able to go to site with the Vogt Power engineers and their representatives and walk down the actual units and observe the challenges that we faced from a engineering as well as a construction standpoint. The customer had a very, very short outage window. So it was actually a 14-day breaker to breaker outage window, which doesn't allow you this very much time for this sort of a retrofit. So what we had to do is we had a multitude of constructability calls within our organization that allowed us to fabricate and also coordinate these pipe spools as well as the pipe supports. If you'll see on the right hand screen, we had pre-installed a lot of the pipe supports so that we were able to just utilizing a crane, lower the pipe spools into position with the hangers already there. They were able to be installed while the units were running, which allowed us to optimize the outage window and be able to perform as much work as we could. Greg, if you'll go back to those first few photos of the candy cane Attemperators up top. So these were actually challenging from a, not really from a demo perspective. We rigged to the candy canes and cut them free from the headers. The challenging portion came in when we were installing the new headers. They actually went underneath a platform that isn't very visible on that photo, but there was very little headroom. So we installed a monorail type system in order to fly this header system into position. If you'll go to the next photo. Yeah, actually that one there. So Greg had pointed out earlier the red arrow where they were seeing some of the cracks, the damage. They had attempted to repair these cracks multiple times. So we actually had to take a lot of that weld off and install our new riser piping onto our header and make a new weld. All of these welds were preheat, post-weld heat treat, and 100% NDE. So in prefabricating these headers with the risers, that limited the amount of fill welds and of course limited our outage duration. Next. And as you can see there, as Greg talked to earlier, the length of pipe was very crucial to the engineering design. So that actual 20-inch pipe, it came probably 3/4 of the way down the side of the unit, which allowed for multiple pipe supports as well as hangers in order to hold that there. And then what really isn't visible there is the actual spray water line that we ran from the ground, and also the installation of new platforms in order to access the key components of these this system here. Next slide. And this is just a representation of our field fabrication. We actually fabricated quite a large section of the Attemperator loop on the ground, and we're able to utilize cranes in order to lift into position. So of course we were able to achieve the outage window the customer needed, and actually had a little bit of spare time to install the external insulation and lagging components on the pipe, and everything was actually flawless and in execution, and we would attribute that to the coordination and the ability to plan this project with the Vogt team. That's all I got, Greg.
Thanks, Tim. So that's it for the first presentation. So I think we're going to kind of open it up for a question and discussion led by Bob. Bob, do you want to take over?
Yeah, thank you. Very nice job, fellas. Are there any questions for Greg or Tim? Don't be bashful, guys, ladies.
I have a question. For this modification on the Attemperators, especially for old units, as you mentioned. Now, is there any modification from Vogt to the user presently that that notifying them that a possible modification on the Attemperators will be needed?
Yes. I think I understand your question as what was there a significant change to the operation of the whole unit in running in this new profile? If I understand you correctly, yes, absolutely. As part of this effort, what we often do as well is we'll run a full thermal study to capture the impacts of this new operating profile. So be it running at lower load or some other difference, yeah, we'll often quantify that. But what is necessary, that was the first step of our process, was kind of running that effort to make sure we understood how the unit was operating, so that when we redesigned it, we captured that whole profile. Does that answer your question?
Yes, and as an addition to my question is, when you say low load, is that an island condition or it's just a cycle in a cyclic condition?
Yeah, that's a great point. I guess I want to differentiate the difference between just cycling, coming up and down, or load following, and then also running at low load. I would call just a normal cycling plant one that maybe comes up once or twice a day, as your demand peaks and then falls off. That's also different or different from a plant who aggressively load follows, right, and is up and down all over the place. And then we also want to contrast that with a plant. What a lot of plants are doing now is instead of cycling and actually turning off, they will just come down to extreme low load. And what that allows them to do is actually respond to the market quicker and get back up to load faster. I'm sure everybody, or I'm sure most of the people on the line are very familiar with cycling and what that does to your unit, the wear and tear. And so what some of this new thinking is that instead of coming all the way down and going through a whole thermal cycle, you actually just turn down to extreme low load. And that possibly does less damage to the overall system from a thermal cycle perspective, but it also allows you to react quicker. So what does low load mean? You know, this definition keeps changing. And it depends on the gas turbine and what you're able to achieve and still be emissions compliant. And that bar keeps going lower. You know, it used to be low load emission compliance was maybe 50% load. You know, I'm seeing extreme examples where people are trying to figure out, can I turn my gas turbine down to 10% load and still be emission compliant? And we're getting very, very close. So that's what we mean when we say running low load. It's the gas turbine's ability to turn down to these extreme levels, and then we're operating the HRSG at those levels.
Thank you very much. It's a great presentation. Thank you.
Yeah, thank you.
You have another question? Now, they did a good job, but they didn't do a perfect job, so there should be a few more questions.
I'd be
got a
curious.
question.
Yeah, go ahead.
Okay.
It looks like the original design had an internal liner, but the new design was installed without a liner. Can you comment on the differences in the design?
Yeah, absolutely. Let me see if I can actually go back to that slide. It might be, you know what? Yeah, this is a little misleading. I apologize for that. Even these ring styles, they still do use a liner. It's typically a little bit different than the liner with the old probe style, which is shown in this picture. The liner is very clearly on the ID of the pipe, and you know, shrinks down, which is actually a design element. You want to increase the local velocity to help atomization. And with the ring style, it still does the same thing. It has a liner system. It's often not quite as long. So yeah, I'm sorry about that. I think this picture is a little misleading.
Gotcha. Thanks.
I have a question.
Okay, we have.
Do you
Go ahead, Fred, then we'll get some of the chat questions.
ever consider reinforcing the elbows downstream of the Attemperator?
Yeah, I'm not sure that I've seen that before. That's an interesting thought. I'd be curious if that really would stand up to any sort of water impingement, right? Have you ever seen that? I'm just curious. Is this a situation you're familiar with?
No, I really haven't. It's just when you were talking through it, just the thought occurred to me, and
Yeah.
And I tend to agree with you. I don't think it would hold up to significant water impingement, no matter what you use to reinforce, like, you know, using something like stellite or some other kind of overlay material inside the
Super hard
elbow.
facing.
I think it would wear pretty quickly if you had impingement.
That's an interesting thought. Doing some sort of overlay there. Yeah, I honestly can say I've never considered that. It's kind of a similar thought to what they tried. You know, they tried a stainless liner, which I guess is along the same lines. and that ultimately didn't stand up. But that's the liner where, you know, you're designed to have a lot more impingement. You know, at the elbow, you certainly hope that it's not a continuous and you know, like a lot of water hitting that elbow. So maybe it would last longer. I'm not sure.
One other question just occurred to me. In the original design, or maybe in the revised design, was the liner, was the annulus between the liner and the idea of the host pipe, was water able to drain from the bottom of that annulus?
Yeah, let me see if this picture, that one doesn't show it. This one
there.
kind of shows it okay. Yeah. So on the entry side at the bottom, it's closed off to oh, I see what you're saying. If water comes down the side, can it drain out?
Yes.
Yeah, that's a great question. Gosh, I'd have to look at the detailed drawing to look at that detail. I don't know off the top of my head. I'm sorry.
Well, one of the problems I've seen before is I've seen where the design of the liner was such that the annulus couldn't drain, and you would actually get, you know, you could get water, a little bit of water residing at the bottom of the annulus, and with attendant corrosion problems.
Yeah. Yeah, I can certainly see that happening. Absolutely.
Okay, that's all I got.
Okay. We've got a question from Yafim. Yafim, can you unmute yourself and ask your question about the image with the leak?
Yeah, my question was about with the variable load, with minimum load, how do you determine the length of the straight pipe downstream of the spray nozzle with the new design? Because as you said, the load varies within the wide range and temperature and all conditions. How do you you really want to design the downstream pipe so that all water evaporates before hitting that first elbow? How do you determine that? How to design that?
Yes, sir. So the first step is to try to get that operating case from the gas turbine manufacturer, exactly what the exhaust flow and temperature is. And what we would do is we would plug that into our thermal rating software program, and we would be able to predict at that load point how much spray flow is required in both the HP and the reheat Attemperator. So that's what the thermal software will do, and that's how we're able to predict the spray flows. But we need that operating case, right? We need it from the GTOEM. Or conversely, you know, if you just try to run there and you capture that PI data, you know, certainly you can use that PI data as well. But you need to know how much spray flow you have, and you need to know your steam flow rate. And then based on those two things, it's a real quick calculation of, you know, do you need 0.1 seconds? Do you need 0.2 seconds? So that's just based on your steam velocity, which is based on your flow rate. So as long as you have the process conditions for that point, we can design everything. But that's the key, is making sure we have those process conditions. Does that answer your question?
Well, with the droplet size and the amount of time needed to evaporate that with the steam flow, do you put that into your calculation? Because the sprays with the different pressures at different operating points is different. So the droplet sizes and distribution of the droplet sizes is all over the place. So do you have that in the calculation of the mass transfer between the steam and the water, and to make sure that all the water sizes, the biggest droplet size evaporate at the lowest load before it hits the first elbow?
Yes, sir. So we won't necessarily do all of that, but we work with our Attemperator vendors to collaborate on that point, right? So we're just an HRSG OEM. We purchase these Attemperators from our vendors, and we work closely with them. But that droplet size, that dispersion pattern, that's their intellectual property, right? And we need them to help us understand what you're asking, right? So they give us a set of guidelines, and we work with them, again, understanding the process conditions to set the design based on that.
Okay, thank you.
Thank you. Greg, there's a question. I don't know who it's from, but it's on this photo at the top of the image we see now, with the leak coming out. You had mentioned that's not from this project, but the question was, what orientation is that elbow, and why is water coming out of it if it's a steam pipe?
Yeah. Gosh, I gotta think back to that project. I believe that is a vertical loop, very similar to the geometry we're considering here, although it is not this specific project. And I believe the problem with this plant is we obviously did not have even close to enough atomization by the time we got to the elbow. So when you have a steam water mixture, what we found is that the water often gets pushed to the circumference. And you can actually put, you can test, you can put thermocouples all around the diameter, the circumference of the pipe at different locations, and you can see the temperature variance and where that water is hanging out. And it's as much a function of the steam water mixture flow pattern within that pipe as anything, So, I mean, you almost have to do some like CFD to get what that flow pattern is. And so I don't think I have a good answer for you as to why the water is hanging out right there. But that's where
I suspect that that's during a hydrostatic test, because there's no way you would be overspraying enough, I don't think, particularly on the intradose, for the water to squirt out. Plus, you wouldn't be operating with the insulation off anyway. So
yeah,
I suspect that that's some test that was being performed. We got another question from Patrick Holt. Patrick, can you unmute yourself?
Yes, sir, I'm unmuted.
Okay, well, ask your question.
Yeah, I just need to know what is the recommended maintenance / inspection intervals for the nozzle and the liners. I'm kind of more on the maintenance side of things at the power plant, and this will be very helpful for us in the future.
Yeah, sure. I think it varies from plant to plant, but I have spoken with some plants who've implemented a very successful program where pretty much on an annual basis, they'll pull their nozzles and they'll actually put it on a rig, and they will spray through them and make sure that they have a good spray pattern, and then reinstall them. While you're out, it certainly would be good practice to throw a bore scope in there, see if your liner is holding up or if it's starting to see cracks. Hopefully you catch that early, before the thing completely lets go and lodges in the pipe somewhere. But yeah, the good plants I've heard, they inspect their nozzles on an annual basis.
Yeah, and annual is the basic recommendation, tempered by how you're operating and what equipment you're running. Some Attemperators and liner designs hold up better than others. So starting point, particularly if you're cycling the unit on and off or coming to low load often, so the Attemperator's turning on and off a lot, annual is the starting place. Now, based on that, you may find after a couple of years that you can back off a little bit depending on what your outage intervals are. But this equipment has such a hard life that the smart money is on doing it more often than not and catching these problems before you have forced outages associated with parts going downstream and cracks in your piping. Very good question.
All right, thank you. I appreciate it.
Thank you.